So in this video, we just want to extend the ideas of gradients and directional derivatives to functions of three variables. And the basic idea is that these ideas and concepts are going to extend to functions of three variables in the way that you expect. So if we have a function f of x, y, z, and we have u hat being a unit vector, well, what's going to happen when we move into a three variable function? Well, u hat's going to need to have three components, so we add in that additional third component u sub 3. We still have parameterized, in the definition of a directional derivative, we still have parameterized x, parameterized y, just like we did in way back in video 1, but we also parameterize z equals z naught plus t times u sub 3. And then minus, hey, we've got to add in that third, that third variable. So our instead of working from a point x naught, y naught, it's going to be a point x naught, y naught, z naught. So the difference quotient is going to look the same that it did for functions of two variables. We just have to extend the concepts out a dimension. And that's going to be the same for a gradient. We defined a gradient of two variables to be, hey, take the partial derivative with respect to x for your x component, take the partial derivative with respect to y for your y component. Well, if we're working with a three variable function, our gradient of f is just going to be defined by taking the partial derivative with respect to z and putting that in for the z component of the gradient vector. And these ideas would extend into functions of n variables in the same way, in the way that you would expect it to. So the directional derivative, it's going to turn out to be that we still define it to be the gradient of f dotted with u hat, but what's going to be the difference is the gradient vector is going to have that third component, and u hat's going to have that third component. So things are going to extend to functions of n variables kind of in the obvious way, and all of the properties that we came up with for the gradient function are going to stay the same. The only thing that's going to be different is that when we have a function of three variables, the gradient is going to be orthogonal to a level surface, which we'll see a little bit later on, instead of a level curve. So in other words, functions of two variables live in three-dimensional space. The graphs are three-dimensional graphs. So when we cut through with a constant plane, we get a level surface in the xy plane. Well, when we have a function of three variables, the graph of it, if you could actually graph it, lives in four-dimensional space. So instead of a level curve in the xy plane, you get a level surface in your three-dimensional xyz coordinate system, and your gradient will be orthogonal to that surface. And we would extend this by adding a third component there everywhere you need it to. The idea is the conceptual pieces for a gradient. In which direction is the maximum minimum rate of change? That's going to be given by the gradient. The size of the max and minimum change is going to be the size of the gradient vector. If you move orthogonal to the gradient vector, there's no change going on. So I don't need to show any examples, I think. I just want to point out when you're doing the homework, when you see functions of three variables, just extend your two variable concepts in the obvious way, and you'll be able to solve those problems.